Hey everyone, welcome back. Another video on numerical differentiation. Last time we talked about a couple of methods. We did forward, backward, central difference method. Today we're going to address these 2 points. We saw with the central difference method there was a limitation in that you could not find the slope at the first and the last points. We could find the slope at first and last points using forward difference and backward difference. Those 2 methods had very poor accuracy. We would like to be able to find the slope at first and last points with the same accuracy as the central difference. So we're going to cook up one scheme for the first, a different scheme for the last, so this is going to be 2 different equations. And then the second thing we want to talk about today is what about higher order derivatives? If we can find the slope, that's like finding velocity or speed. If we can find the second derivative, this would be a numerical acceleration term. So how can we formulate f double prime? And again, we want to do this one with a high level of accuracy as well. Okay, let's start with number 1, and we're going to look at first and last points. Recall that in the last video, when we were deriving forward, backward, central difference methods, we used Taylor series expansions. Now, in those cases, those algorithms ended up looking a lot like the intuitive solutions we came up with, right? In these cases, we're going to use these Taylor series expansions to come up with some more complicated approaches. So what we're looking for here is we want the slopes at the first and the last points, right, with higher levels of accuracy. So I've gone ahead and I've taken f of x minus h, and I've written out the Taylor series expansion. You should already have this in your notes from the previous video. Now, if we're doing x minus h, clearly this is the point before x. So we cannot, whatever approach we're about to do, this is for the last point, not first point, simply because we need data ahead of time. So we're going to use f of x minus h. And also we're going to use f of x minus 2h. So if f of x minus h is the point before, f of x minus 2h is the point before that one. Here's the expansion, Taylor series expansion for this point. It's f of x minus 2h, f prime of x, plus 2h. The 2h is going to go into the h squared. The 2 is going to get squared, so that makes 4h squared over 2 factorial multiplied by f double prime of x. And then I'll go ahead and write in the third term. So this is going to be 8h cubed over 3 factorial f triple prime x plus dot dot dot. Okay, remember the goal. The goal in this is to calculate the slope. Right? We want f prime. We know we're going to have to truncate this series, and what we have found is that if we truncate between the first and second derivatives, we're going to get a certain amount of error. And we were able to, central difference, we were able to truncate in between the second and third derivatives, and that gave us a more accurate answer. Because we had less error, we were able to truncate at a higher order term. So the goal here is to use these 2 equations somehow to isolate the slope, and we would really like to truncate between the second and third derivatives. That would give us the same accuracy as central difference. So what can we do? Well, let's call this one equation 1, and let's call this one equation 2. And we need to manipulate these equations somehow to get, really what's going to happen is we're going to have to make this f double prime cancel. We're going to have to make these go to 0 so that we can then truncate here and retain the f prime. Now, if we want to make these cancel, clearly we can't just add them, and we also can't just subtract them, right? Because there's 1 here in equation number 1, and then there's 4 in equation number 2. What we could do, though, let's try this. Let's try taking equation number 1 and just multiplying it by 4, and then subtracting equation number 2. Something is going to happen with all of these terms. We're going to sort out that math, but right off the top, we can look at this approach And we can see that that's going to make this 4h squared, and that's going to subtract 4h squared, and that's going to make this second derivative equal 0, so that when we truncate it, now we're truncating at the third derivative. So let's do the subtraction. So this is 4 f of x minus h, and then minus f of x minus 2h. Again, that's just the left-hand sides of these equations. We're going to have 4 f of x minus 1 f of x, so 3 f of x. We're going to have a negative 4 here in equation 1, and then we're going to subtract negative 2, which means we're going to add 2. So if this is negative 4 and then we add 2, what is left over is minus 2h f prime x. And then we could go through all these third derivatives, etc. I'm just going to say dot dot dot. The convenient part here is that we were specifically able to make this term go to 0, so that when we truncate this, I'm going to cut it here, which means this equals becomes now an approximate. Okay, remember the goal. The goal is to isolate f prime. Well, we can use this now to isolate f prime. We could take the 3 f of x, we can move it to the other side, recognize there's going to be a negative 2h on the f prime, and then we divide by the negative 2h. When you do all of that, here's what you get. We're solving for f prime of x. This is approximately equal to, we're going to have 3 f of x minus 4 f of x minus h, and then plus f of x minus 2h, and then that quantity is divided, that quantity is all divided by 2h. Okay, this scheme, this lets us solve for f prime. This is going to be a higher accuracy method because, again, we're truncating here at the third derivative now, so this should be this should give us the same accuracy as central difference. And by the very nature of the points that we chose, you need information, you need f of x, you need f at the point before it, and you need f 2 points before it. That means this method, we can only use this method, or really this method is a tailor fit for the last point in your data set. We're about to come up with the algorithm for the very first point. You would use central difference method for all the points in the middle. And then when you get to your final data point, here is the algorithm to handle that. There is a question in your upcoming lab that specifically says solve for the first and last points with the same accuracy as the central difference. That is this algorithm, or this calculation. Okay, so here it is for last point. Let's do this again and let's look at first point. Again, we're going to start with Taylor series expansions. Here is the expansion for f of x plus h. You should have this in your notes from last time. We're going to do something similar to what we just did. Notice now we're looking at x plus h. That means that we need the data point in front. We can use this approach for the very first data point. Now, we're doing f of x plus h. Let's also do f of x plus 2h. So the point in front and then the point in front of that one. And let's write out the Taylor series for this. So this is f of x plus 2h f prime of x plus 2h squared, so 4h squared over 2 factorial f double prime, and then the next term, 8h cubed 3 factorial f triple prime x plus dot dot dot. Okay, so what are we gonna do? Remember, the goal is f prime. We want to truncate it in between the second and third derivatives. That means we need to make the second derivative go to 0. Clearly we can multiply equation 1 by 4. So 4 times equation number 1, and then subtract equation number 2. All right, if we do that, here's what we get. 4 times f of x plus h minus f of x plus 2h. There's going to be 4 f of x's minus 1 f of x. We're going to get 3 f of x. We're going to have 4 h f prime and then minus 2. So that leaves 2 plus 2 h f prime of x. The f double primes, these are going to cancel. We could tack on these higher order terms. We could write them out explicitly if we wanted to. I'm just going to say dot, 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 because again, we're going to truncate those. So let's cut these off. And by cutting those off, the equals becomes an approximation. Now, what's the goal? The goal is to solve for f prime. So we can just move the 3f of x to the other side and then divide by the 2h. When you do that, here's what you get. F prime of x, this is going to equal minus 3f of x plus 4 f of x plus h, and then minus f of x plus 2h, and then this quantity is going to be divided by 2h. Okay, here then is your scheme, your method for finding slope at, this is now the first point. Use this approach to calculate slope for the very first data point. Use central difference. Hey, cut out. Use central difference for all the points in the middle, and then use the method I just gave you for the last point. Okay, let's move on now. Let's talk about calculating higher order derivatives. So, last topic of the day. We're still doing numerical differentiation. This time we want to find f double prime. F double prime would be acceleration, right? The second derivative. And as always, we want to do this with a high level of accuracy, which means we need to truncate as high of the highest order terms as we can, right? So what I have written down now are two equations. Let's call them number 1 and number 2. And you can see number 1 and number 2, we've seen these several times. This is the Taylor series expansion of f of x plus h. Here's the Taylor series expansion of f of x minus h. One thing, before we even move on, immediately, what do we know? We know that if we're using the point ahead and we're using the point behind, then this is kind of like the central difference scheme, the same limitations. Whatever it is we're about to do, this can only be done for points in the middle. These cannot be done for first and last points. So the goal now is to isolate f double prime, right? That's the new goal. So this time we want to keep these. So clearly we need to truncate this series at least between the second and third derivatives. So we need some way to calculate this. Now, one thing to take note of is that we would really like, whatever we're going to do for f double prime, we would really like the f prime to not be involved, because consider all we have are numerical approaches to calculate f prime at this point. All we have are numerical approaches. Again, this process is applied to data. So you have all of these f of x's and f of x minus h. This is the data that you collected. You don't inherently have f prime. We're developing methods to calculate f prime, but we don't explicitly have it. And we know that any calculation we do of it has a little bit of error involved. So it would be really nice if we could isolate the f double prime and not have an f prime involved. Okay, that means we want f prime to go to 0 and f double prime to not go to 0. So since on the expansion of f of x minus h, these odd term derivatives, they all go negative, what if we just add these two? What if we do 1 plus 2? Okay, let's just do 1 plus 2. If we do 1 plus 2, the left-hand side, f of x plus h plus f of x minus h. Next, the f of x's will add. This is 2 f of x. And then these, the f primes, these are going to cancel. These will add. So this is now, well, let's think of it this way. What is 2 factorial? 2 factorial is 2. So this is h squared over 2 and this is h squared over 2. We add them together. We get h squared f double prime of x plus, what's going to happen to the third order terms, this third derivative? Well, one's positive, one's negative, so these are going to cancel. So when I put dot, dot, dot over here on the right, understand that there are 0 f triple primes, and then it's dot, 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 right? So we're, when we go to truncate this, which, there we go, by truncating it, really what we're doing is we're cutting off the fourth derivative and higher, which means this method should be fairly high accuracy. At this point, we can just solve for f double prime, move the f of x to the other side, divide by h squared, right? So I'm going to erase the top. F double prime of x. Since we did a truncation, we know that this exact becomes an approximation. So you move this to the other side and you divide. Here's what you get. This is approximately equal to f of x plus h plus f of x minus h minus 2 f of x, and then this quantity is divided by h squared. Okay, there is your numerical calculation for f double prime. Again, we talked about the limitations. Cannot be applied to first point, cannot be applied to last point. So this one has similar limitations to central difference. Okay, and that's it. There's your theory videos for numerical differentiation. We have one more video that I'm going to do with numerical differentiation. It's going to be the code implementation. So I'm going to do another screen capture video. Just keep an eye out for it. But you should be equipped now to go solve all the problems in the upcoming lab. So best of luck. Let me know if something comes up. I will see you next time.